do a second session of probability here. We're going to switch from Venn diagrams to contingency tables. So remember we said that we're going to let A be an event and B be another event. And then we also defined this little C up here as the complement of A. So A did not happen, B did not happen. So if we make a 2x2 table here, we see that we can have the intersection here of A and B, where A happens and B happens. And then going down the column here, this would be where the complement of A happens and B happens, so that intersection. And then moving along, we have A and not B, along with not C and not B, sorry. So I've drawn little dotted lines around the outside, and we'll do an example in just a moment, because whenever you see these kind of tables set up, or you see an opportunity to make it, it's always good to put these sidebars in, these side totals. So for example, let's say that we had 5, 8, 2, and 6 here. So what I would want to do is go ahead and total these guys out. So going down the column here, we have 7. Going down this one, 14. Going across, we have a total of 21. Going across on the top here, we should have 13. And going across here, we have 8. So now that we've got these together, someone might ask us, what's the probability that A happens? Well, where does A happen? A happens here, A happens here, so the total where A can happen is 13. Now, but we want a probability. 21 here is our total space. So 13 over 21 would be our answer for the probability of A. Now, what about the probability of A intersect B? Well, with our contingency tables, we find where does A intersect B? Right there at 5. So that probability is going to be 5 divided by 21, the total here. Now here comes the tricky part, probability of B given A. Now the easiest way to look at this is say backwards like we did in the previous exercise. Given A, that's this row here, so this is our new space, and we're not concerned with not A any longer. What is the probability of B, which is 5 here? So, since we know we went backwards here and said, all right, well, A is what we're interested in. What's the probability of B given that A is occurring? Then we know our denominator is 13. And then working back to the B here, what's the probability of B given we're in the A space? That would be 5. So we have 5 over 13. Now, a quick, just work on our skills here. What if somebody asks us, what's the probability of A complement? Well, we could go through and do it like we did last time, or recognize that the complement of A is just the opposite. So, if we go 1 minus the probability of A, we'll get 1 minus 13 over 21. Boom. So notice, when we're doing these guys, the conditional probabilities, the probability of B given A is not equal to the probability of A given B. Make sure you work that out for yourself. A and B are what we call independent. That's a term you'll want to look up if the probability of A given B is equal to the probability of A by itself, and the probability of B given A is equal to the probability of B. Now the way this works out is all we're saying is that if the probability of A given B, so if we're given the information that B happened, what's the probability of A? If it's equal to the probability of A, that just means that the probability of B had no impact on helping us decide that. And the same goes here as well. So another rule that you're going to want to know, which is our addition rule, is the probability of A union B. So what's the probability of both happening, or either of them happening? So we've got this guy. Let me go ahead and draw another Venn diagram for this one, and I'll put it over here. So when we draw this out, if this is our B, and this is our A, and we add the probability of A and the probability of B, what we end up shading in is all of this space for A and all of this space for B. But what you'll notice is that intersection piece in the middle, right here, got counted twice. So that's why we have to take this piece off right here and take off the probability of A intersect B. However, if we know that A and B are mutually exclusive, that's another term you're going to want to know, then that means that A and B intersected is null. That means they don't intersect. So it'll look more like this. And since there's no intersection, if we calculate A union B, and that probability, then that means we only have to calculate the probability of A plus the probability of B. So one last one here, A intersect B, if we want to calculate that, we have two different ways, and this is part of our multiplication rules. If they're independent, then we can just do probability of A times the probability of B. If they're dependent, then we have to do the probability of A times the probability of B given A.